there we have it. And I'm just going to pick apart the graph a little bit here. So another way to think about an inverse function is that the independent x and the dependent variables for f of x switch to become the independent variable of f inverse of x, or sorry, the dependent variable and the independent variable of f inverse of x. And essentially, the x's and the y's switch. And since the x's domain is x, range is y, since if this is for f, the domain and the range of f of x then become the range and the domain of your inverse. So your domain becomes your range, and your range becomes your domain. Now that is just a little interesting fact that may come up from time to time. But I am just, some of you guys may be rolling your eyes at home and telling me that I'm made a fundamental error in my work, and I actually have. However, not all functions have an inverse function. Now, the word function is important. I will say all functions have an inverse, but is that inverse a function itself? I am not convinced of it. So in order for f of x to have an inverse function, f of x must pass a horizontal line test. So let's go back to this previous example up here. In this previous example, f was all my original points. And indeed, f was a function. It passed the vertical line test. However, the green points, or the inverse points, they are not a function collectively. And that's because they fail the vertical line test. So I guess what I'm trying to say, is there a magical way that you could test if a function has an inverse function? Yeah. If you test if the original function passes a horizontal line test. Horizontal line test will then in turn turn into a vertical line test when you're testing the inverse. All right, enough of this. Let's continue on. So very quickly here, example 1. So I'm going to be going over example 1. You'll just have to trust me on this. What I really want to express to you is the whole notion that not all functions have an inverse function. So here's my graph. F of x is equal to x squared. Now, if you're going to have to trust me on this. I'm going to draw the identity line. And the identity line is going to look somewhat like this. If I take all my points along this parabola, right? This is 1, 1. This is 0, 0. This is negative 1, 1. If I take all these points and reflect them about the identity line, they're going to turn into this function. Now, I think it's quite evident that the inverse function here, the green function, oh, I can't even use the word function. So the inverse is indeed the inverse for f of x, but the inverse itself is not a function. So I would probably not use this notation. But this is only an introduction lesson. So here, you are very familiar with a parabola. A parabola will fail the horizontal line test because there's two arms. Now, let me go on to the next example. We're going to sketch g of x, where it's g of x is equal to x squared, and my domain of my function is simply going to be x greater than or equal to 0. In other words, what have I done? I have one arm of my parabola. So with this parabola, it passes the horizontal line test. And indeed, this function will have an inverse. So you'll have to trust me again. So here's my identity line. My inverse function simply will look like that. So if this is g of x, the inverse is g inverse of x. All right, we are almost there, I promise. So I'm hoping that really from the above, I just want to introduce you to the idea that this is still a reflection about the identity line, and we'll see this maybe Thursday or Friday, that not all functions, we have to be careful when we derive an inverse function. But don't worry, in grade 11, generally I take care of that for you. You don't really have to worry about it, but it's very important to recognize. All right. Let's do the next example. In this next example, we're going to read. We're going to algebraically find the inverse function of f of x is equal to 2x minus 3. So I'm just simply going to do this. First thing, I am going to, just for notation's sake, let f of x is equal to y. I find it much, much easier to deal with x's and y's. Now, I'm still working on my themes of inverse functions. So very quickly, I'm just going to say switch x's and y's. This actually should say replace x with y's, y's with x. And when I do that, I'm going to create the equation x is equal to 2y minus 3. There is my inverse. What have I done? Just switch the x's and y's. That's it. However, we always like to isolate y to one side. So now here's just algebra. Isolate y to one side. So allow us to do that. The next, to get y all by itself, I would probably add 3 to both sides. The next step that I would do is I would probably divide both sides by 2. So really, this is just isolating y. And so we're going to be isolating y. And essentially, I'm almost done here. So y is isolated. So I'm going to write y is equal to x plus 3 divided by 2. And now this is my inverse function. So I'll just replace y with f inverse of x because it is the inverse of f of x. So let's just I'm going to pause the video here in about a minute's time. We've done a little bit of work. However, if I said to you at the beginning, what is the inverse of taking something, multiplying it by 2, then subtracting 3? A lot of you would have been like, well, I know I have to add 3 because it's the inverse of subtracting 3. I'm going to have to divide it by 2. So intuition goes a little bit into this. But there are some unexpected surprises.